Before we start talking about the main subject at hand, which is going to be adding and subtracting rational expressions with uncommon denominators, I want to take a few minutes, like I have been in the previous worksheets, and show you how this works with fractions. Because if you can understand how it works with fractions, it's going to go a long way in helping you understand how this works with the rational expressions where we incorporate algebra. So practice with fractions. Recall the steps for adding and subtracting fractions with uncommon denominators. You have to find the LCD, which is the least common denominator, okay? So that is basically the smallest expression that all of your denominators divide into evenly, okay? For us, it's going to be the smallest number all of your denominators divide into evenly. Once you have the LCD, you then rewrite all of your fractions so that they are equivalent forms of that fraction, but the denominator is the LCD. And then you just follow the steps for adding and subtracting fractions that have common denominators. You add or subtract the numerators, you keep the new common denominator, and then you factor and simplify at the end, okay? So let's look at example one. It says find each sum or difference. So I am going to go through this step by step so you can later relate the steps I show you here to what's going to be happening with the rational expressions. So we have 3/10 plus 7/12. We need to find an LCD, okay? And there's this table that you can use to find an LCD. Now, when it comes to just dealing with fractions, the table can be helpful, but it's not quite as necessary. However, with rational expressions, you really do kind of need to understand how the table works, okay? So what you do to create this LCD table is you find prime factorizations of each of your denominators. For us with rational expressions, we would just factor them, okay? But for 10, we would write that as 2 times 5. For 12, we would start by saying, okay, that could be 4 times 3, but 4 is not prime, so we'd write that as 2 times 2 and then times 3, okay? So that's how you'd start. You'd find these factor trees or these prime factorizations. You then create a row in your table for each denominator and then a row for the LCD. So then you want to fill in one of the denominators as a prime factorization into the table. And I usually do the denominator that has the most factors. So when I look at 10 and 12, 10 has 2 factors, but 12 has 3. So I'll generally start with 12 just because it has more factors. So 12 is 2 times 2 times 3. That's great. The issue is now that I have a 2 in this first column, that's the only type of factor that can go in that column. The second column already has a 2 in it. That's the only kind of factor that can go in the second column. And the third column can only have 3's in it. So what we want to do is we want to fill in all of the factors from 10 into this table. We want to overlap as much as we can and only start new factors when there's not a column that that factor could already fit into. So I have a factor of 2. Well, that 2 could go in either of the first 2 columns because they're 2 factors, or they're 2 columns, or whatever you want to call it. And then I have a factor of 5. Well, the 5 cannot go here because that's a 2's column. The 5 cannot go here because that's a 3's column. So I would have to start a new column for my 5. And then basically what I do to get my LCD is I take the representative of each column. So what type of column do I have? Well, the first column is a 2, so I bring down a 2. The second column is a 2's column, so I bring down a 2. The third column is a 3's column, and then the fourth column is a 5's column. The product here is my LCD. So let's see what we get. We get 2 times 2 is 4. 4 times 3 is 12. 12 times 5 is 60. So my LCD is 60. Okay. So what I want to do now is I want to rewrite both of my original fractions into equivalent forms that have 60 as the denominator. To do that, I ask myself, what would I take my current denominator by and multiply it to get the new denominator? So what would I multiply my first denominator by to get the new denominator? Well, if my first denominator is 6 or 10, whoops, if my first denominator is 10, to get 60, I would multiply it by 6. But here's the issue. If I multiply the denominator by 6, I can't just ignore the numerator. I have to multiply by numerator by 6 as well, because what I'm really doing is multiplying by 6 over 6, but 6 over 6 is really just equal to 1. So technically, I'm multiplying this first fraction by a weird form of 1. I'm not changing its value, I'm simply changing its appearance. So my first fraction becomes 18 over 60. Now my second fraction has a denominator of 12. What would I multiply 12 by to get 60? Well, I would have to multiply 12 by 5. But again, if I multiply the denominator by 5, I have to multiply the numerator by 5 because that allows me that weird form of 1. 5 divided by 5 is really 1. So I'm technically multiplying 7/12 by 1. Multiplying by 1 doesn't change the value. We're simply changing the appearance. We're making these two fractions something that we can work with. So my second fraction becomes 35 over 60. So now I have 18 plus 35 over 60. Well, let's see what 18 plus 35 is. We should get what, 53? Let me double check. We do, in fact, get 53. So I have 53 over 60. Well, 53 and 60 don't have any common factors. The factors of 60 would be, well, 60, 1, 2, 30, 3, 20, 4, 15, 12, 5, 6, 10. None of those are factors of 53. So this is our final answer. Okay. Let's do the same thing, but this time for 7/10 minus 3/16. Okay. So let me erase a few things here. We're going to do our factor trees up here again. Well, luckily, one of my denominators is 10, and I already have a factor tree for 10. So my prime factorization for 10 is 2 times 5. Now 16, I know I can write it as 4 times 4, but the 4s are not prime, and we always want to get this to where we have all prime factors. So 4 is 2 times 2. 4 is again 2 times 2. And now I'm going to start my table, okay? So I have denominators of 10 and 16, and then that's going to be a row for each of those, and then I need a row for my LCD. And I fill in one of my denominators. It legitimately does not matter which denominator you start with. Me personally, I always start with a denominator that has the largest number of factors. In this case, it would be 16. So 16 is 2 times 2 times 2 times 2. That means the first 4 columns of this table can only have factors of 2 in them. So I want to take the denominator of 10, I want to write out its factorization in this table, and I want to overlap as much as I possibly can. So that 2 that I have could go in any of these 4 columns. So let's say I put it here. The 5, however, cannot go in any of these 4 columns because those 4 columns only take 2s. So I have to start a new column for my 5. And now I want to drop down each representative, so each type of column, what type of column it is, what factor it takes. So the first column has a 2 factor, the second has a 2 factor, the third and fourth have 2 factors, and the fifth has a 5 factor. We multiply all of that out and we get what, 16 times 5, is that 80? It is in fact 80. So our LCD here is 80, okay? So we then ask ourselves, what would I do to make each of these new, or these original fractions, new versions of those fractions that are equivalent but have the LCD? So we have to look at our denominators and ask ourselves, what do we multiply these denominators by to get the LCD? Well, my first denominator is 10. I would need to multiply 10 by 8. But remember, if I multiply the denominator by 8, I have to also multiply the numerator by 8 because we're secretly multiplying by a weird form of 1. When you multiply by 1, you don't change the value. We're simply changing the look of this fraction. And then to get 16 into 80, or to get 16 turned into 80, we would have to multiply 16 by 5. So I want to multiply 3 and 5, or 3 and 16 by 5, because 5 divided by 5 is really equal to 1. We're secretly multiplying by a weird form of 1. So our new fractions become 56 over 60 minus 15 over 60. Well, that gives me 56 minus 15 over 60, which is really what, 41 over 60. And, or not 60. I hope somebody at home was yelling, stop, wait, you have a mistake. 56 over 80, 15 over 80, 56 minus 15 over 80, and then that ends up being 41 over 80. And 41 has no common factors with 80, so that's as simple as it's going to get. So you have to remember these steps for adding and subtracting fractions that have different denominators, because these same steps are going to come up when we talk about rational expressions, okay?